already nationwide. You can't find it.
All right, so problem of day 16 is one of my favorite reactions. It's actually one that Klein chose for whatever reason to omit from our textbook, but it's a personal favorite. And I tried to give you guys some guidance for this reaction. And the first step said you need to form an imine or iminium ion. Second step, you need to form your enol from your ketone. And then you need to add your enol to your imine or iminium ion. And then last step's deprotonation. So let's break this down into steps. First step, we've got formaldehyde, which is a great electrophile because it's a aldehyde with very little stabilization. And if we take this and we add catalytic acid and we add our amine and we drive off water from this reaction, we can form our iminium ion. So this is review from a previous chapter. And because we're under acidic conditions, it will actually stay at this iminium ion, right? All right, step 2, we need to form our enol from the other ketone. So our ketone in this case is acetophenone. And we're under acidic conditions, so are we going to get the enolate?
Yes.
No. So in this case, under acidic conditions, you'll have an enol instead of your enolate. It's important to remember that these are actually equilibrium conditions for this. And then in the next step, it's kind of unique, but what happens is that these will attack each other. So your enol can add into your iminium ion and kick up electrons onto your positively charged nitrogen. So this is step 3. All right, and then step 4 was adding in our sodium hydroxide, which just deprotonates our ketone. And there we go, we've got our final product. We're one methyl group away from having made methamphetamine.
Whoa, wait, what?
These are actually a very popular class of drugs. Anytime you see phenethylamine, these tend to be psychoactive. If you took off this ketone and added on a methyl group on there, you'd be right at methamphetamine. But we're not going to get into that chemistry.
I mean, let's get into that. Why don't
We might get into that when we cover amines, though.
Hey, now you got it.
Yeah, I piqued your curiosity here. Yeah, phenethylamines are very, very common pharmaceuticals.
I know. What's MDMA? Can we draw out MDMA?
All right, so let's calm down here. We're going to continue on to the Malonoic ester synthesis. And the Malonoic ester synthesis is a branch off of our alpha carbon chemistry. It's very, very similar to what we've seen already. But let's start with the overall reaction. In the overall reaction, we're going to take an alkyl halide and we're going to actually attach this alkyl halide onto a new group and form a carboxylic acid. So it's a pretty nifty conversion between an alkyl halide and a carboxylic acid. All we're doing is we're adding a new alkyl group onto the alpha position of acetic acid, essentially. So let's do the overall reaction mechanism. And in this synthesis, you always start out with diethyl malonate. Oop. This is diethyl malonate. So if you guys remember the oh my, such good apple pie, this is similar to malonic acid, and so it's called diethyl malonate. And then in the next step, what we're going to do is deprotonate it using sodium ethoxide. And which protons will it grab?
The central ones.
Yeah, the central ones. They're really the only alpha protons we have. And because they're between two carbonyl groups, they're very, very acidic. Okay, so now we've got our enolate. And with our enolate, we can now add in our alkyl halide. So I'm going to abbreviate this again with the blue. And so our enolate can come attack our R group, kick off our leaving group. This is typical SN2 chemistry. Will it work if R is a tertiary carbon? No, it has to be a primary or methyl group carbon typically in order for this reaction to work well. So it follows the same SN1, SN2 rules that we've previously learned. So now we've got our R group attached. But now I don't want those ethyl esters anymore. We want our final product to be a carboxylic acid. So how can we change those to a carboxylic acid? Yeah, we can do hydronium on there. I'm not going to show all of the steps for this because it's quite steppy to do it for both of these. But if you go back to our carboxylic acid derivative section where we covered hydrolysis of esters, you can convert esters to carboxylic acids quite easy. And we still have this R group hanging out on there. Because it's a multi-step synthesis, or multi-step mechanism, I'm just not going to draw out all the steps. All right, I'm going to draw this slightly differently, and you'll see why here in a second. So I'm sticking the carboxylic acid OH up closer. Why might this conformation be more favorable? Yeah, it can hydrogen bond to itself. So in fact, it's more accurate to draw it in this conformation than the linear conformation on the right. Now, the cool thing we can do is we can add in some heat, and we're set and ready to go. This bond will grab a hydrogen. This bond will clamp down. Sorry, let me double check mine. Oh, I'm messing up here. Sorry, guys. This bond will clamp down, this bond will jump over, and then this will jump up. So it's a cyclization reaction. So let's take a look at what comes out here. So that carbonyl grabbed the oxygen, so it's now an alcohol. We still have an R group here. And then we've got CO2 gas. So we're evolving CO2 gas off of this reaction. I'm going to actually just write CO2. And this is a really nice reaction because this will bubble out of the mixture. And this is called a decarboxylation. Okay? So we're also at an enol, right? Sorry, this should be the blue R. And is the enol very happy as the enol? No. What will it tautomerize into?
Back into a carboxylic.
Yeah, in this case, it'll tautomerize into a carboxylic acid. The equilibrium is very, very favorable. And we've installed that R group in the alpha position of acetic acid. So it's kind of a nifty synthesis in order to make functionalized carboxylic acids. All right, the question I have for you guys, though, is let's go back up to the synthesis portion. We deprotonated diethyl malonate in the first step and formed an enolate that alkylated using the alkyl halide, but we still have alpha protons on there. Could we maybe dye substitute this? What do you guys think?
Yes.
Yeah. So you can actually get dye substituted alpha substitution off of a carboxylic acid, and let's take a look at one of those examples. So let's take diethyl malonate. And in the first step, we're going to react it with sodium methoxide. Second step, we're going to react it with our normal alkyl halide. I'll call that our blue R. Then we can keep on going. Do more sodium methoxide. And then in the fourth step, we can add in a new R group. And so we can dye substitute our ethyl malonate. And then in the next step, if you think about our previous synthesis, what do we need to add? We need to change the esters into carboxylic acids. What reagent did we use? Yeah, just an acid, right? So H3O plus. And then how did we drive off the CO2? Just crank up the heat, right? It takes a fair amount of heat to drive that cyclization reaction, but when you do that, you can drive off CO2. And your final product for this reaction will be a dye-substituted carboxylic acid, where one of these is a blue R and one of these is a red R. Can we ever get 3 alkyl groups off of the alpha position? No, because we only have 2 alpha protons that we can alkylate or deprotonate and then alkylate. So this is the most complex you can get using the malonic ester synthesis. It's a pretty simple but versatile reaction. There's also a cousin to this reaction. It's pretty similar. Is it okay if I switch pages?
Wait, so what's stopping it from deprotoning the extra alpha proton before you add the acid?
So like you're talking about in the previous example?
Yeah.
So in this one, we can control stoichiometrically how much of our alkyl halide we have. Yeah, and same with our base, too.
Okay.
Yep. All right, so let's go on to the next reaction, which is closely related. This is the acetoacetic ester synthesis. It's kind of a mouthful. So in this reaction, we're again going to take an alkyl halide. But this time what we're going to do is we're going to make a ketone instead of a carboxylic acid. Let me slide this down. All right, so let's look at the mechanism for this reaction. Instead of using diethyl malonate, we're actually going to use a variant of it. Where only one side is an ester and the other side is a ketone. And then in the first step, what we're going to do, just like before, we're going to react this with sodium methoxide. We're going to deprotonate one of these alpha protons. Let me clean this up. And then just like before, we can react this with our alkyl halide in the next step. And our enolate will do a nucleophilic attack, kick off our leaving group. And now we've got alpha substitution. Now in the next step, we said we can add in acid, but in this case, we only have one ester that we can hydrolyze off. And just like in the other example, we can draw it in a different configuration. Let me actually make this a bit shorter. So we're going to spin around that carboxylic acid. We still have our R group off of there. Then in this one, we're going to have that clamp down, clamp down, clamp down through a decarboxylation that requires a fair amount of heat. So we get CO2 gas that will bubble out of solution. Let me draw my double bond better. And we still have our R group on there. And this will quickly tautomerize back to our keto form, which is much, much more favorable. So it's a pretty similar reaction to what we just saw, but in this case you can form a ketone. So on your problem of the day, I gave you guys some exercises where you can try practicing on these. If you can, try to draw out the full mechanism just so that you can practice your tautomerization and all of the saponification or hydrolysis of ester steps. But I think that's where we're going to leave the acetoacetic acid synthesis in terms of the basic stuff. But let's go on to a slight variance of it.
Do you always get the Z outcome first, or does it matter?
It doesn't really matter in this case. You normally get the one with the least amount of steric clashing, but it's going to quickly tautomerize to your ketone, so it doesn't matter a whole lot. All right, let's do some practice. And I want you guys to predict the product for these. So step 1, 2, 3, 4, and 5. This one's a doozy. All right, steps 1 and 3 follow sodium methoxide. Step 5 is the acid and heat. And then in step 1, I'm going to add in an alkyl halide. And step 4, I'll add in an alkyl halide. All right, so if this were on a quiz, I would have my box with a little 3 or 4 next to it. So I'll give you guys a minute. Yeah.
Are the R groups the same, or are they different?
They're different. That's why I have colors. So we'll call this even R prime for those of you using non-colored pencils. Yep.
You would get a picture of product.
Well, let's talk about that. Let's first try to determine what our product would look like.
I mean, I know there's one that obviously alpha protons are much more acidic, but there's still there alpha protons on both sides.
Yeah, there are alpha protons on both sides, but would the methyl group alpha protons be that acidic compared to the internal ones?
I'm saying that one's a lot more acidic than one still.
In this case, sodium methoxide isn't a super strong base. It's not like LDA. So it would go after the most acidic protons available, which would be the internal ones. All right, raise your hand when you think you've got the product. Couple hands. All right, so it's just like our malonic ester synthesis. Whoop. But one of these R groups will be coming off the alpha position, and then the second R group will be coming off the alpha position. It can be quite complicated to control stereochemistry for these reactions, and we're not going to get into that for the alpha stereochemistry.
There's no alcohol in it?
Nope. So it's just like our malonic ester synthesis, but in this case, instead of a carboxylic acid off the end, we just have a ketone. Yeah, so it's an alpha substituted ketone. All right, now let's kind of do a different one. This one's a little bit challenging.
Professor, if you don't have a carboxylic acid, why do you have it?
So let's go back and look at our product from the malonic ester synthesis. And in this one, we had an alpha substituted carboxylic acid. In this one, we have an alpha substituted methyl ketone. So
I know I see that. I thought the point of the last step was to create the carboxylic acid.
it's to create the carboxylic acid from the esters so that you can do a decarboxylation, right? So the decarboxylation won't work unless you have the carboxylic acid. So that's the main purpose of adding the acid in, is to hydrolyze your ester. Yep.
So you said there's going to be a space added, but it's going to be since the R groups are coming out of one carbon, we're not going to get
Into the stereochemistry for this. It gets a lot more involved. For right now, you should just know that you can di-substitute the alpha position off of a ketone. Yep. All right. Let's do another more tricky one. You guys ready for this? What will this do? Something tricky. You guys remember what we called this yesterday?
Some
Some dude's name that you're jealous of?
Yeah. Diekman. Stealing all the easy reactions and making it harder on the rest of us. So we've got alpha protons that we can deprotonate. Oh, shoot. So now we have a negative charge right here. This negative charge can actually attack itself. And when we do this, we get a 5-membered ring, if you remember from yesterday. And then what's the next step? No, we can actually do something before the deprotonation. Or protonation. Yeah, we can shove off the leaving group right next to it. So this was an example of the Diekman cyclization. All right, so we've got our product that we figured out how to make yesterday, but let's do a variant from today. Let's add in acid and heat. Oops, sorry, I'm skipping steps. Oh my goodness, I apologize. First step, let's do deprotonation. I jumped ahead in my notes. Where will it deprotonate? Yeah, in between the two carbonyls, we still have an alpha proton. Sorry, I completely jumped ahead in my notes when I was looking. So we still have an alpha proton here that this sodium methoxide can come around and grab. All right, now let's alkylate it. And when we do that, we can kick off our leaving group. All right, now let's add in our acid and heat. That's where I was jumping the gun. What will your final product look like here? What?
He said, I hate this naming crap. He didn't ask you to name it. You just said what the problem is.
Oh, did just turn that into a carboxylic acid?
Yeah, so when we add an acid, this ester group will be hydrolyzed to a carboxylic acid, and then when we add heat, what will happen to this entire carboxylic acid? It'll pop off as carbon dioxide, right? So in this case, our final product will be a ketone with an alkyl group coming off of the 2 position. So actually a cyclopentanone with a alkyl group coming off of the 2 position. So you can use combinations of the Dieckmann cyclization and the Malonoic ester type synthesis in order to form a bunch of alpha substituted rings and things like that. With the Dieckmann cyclization, what ring sizes are preferred again? 5 and 6. They're always the preferred ring sizes for these reactions. All right, so I think we've kind of hit alkylations as much as I cared to hit them. Let's go on to a new topic. Let's do conjugate addition reactions. And this is kind of drawing from our memory bank from last term. Which of these is more stable and why?
The left one.
What? Yeah, left one's conjugated and therefore more stable.
Those are different molecules.
Yeah, exactly. But if we think about the conjugation for the one on the left, those pi bonds can talk to one another, right? They can electronically communicate. The one on the right, because it's got an sp3 carbon right there.
Those are different molecules.
Yeah, I'm just looking at overall electronic stability. When you have alternating double single bonds, those molecules tend to be much, much more stable. And we went over a bunch of reactivities for these. We can also kind of pair this up to what we've been studying this term. And we can look at alpha beta versus, I guess, beta gamma unsaturated ketones. Alpha beta unsaturated ketones are conjugated. Any other form of unsaturation doesn't lead to conjugation for these molecules. And so if we think back to our chapter about conjugation, conjugated molecules undergo different reactivity, right? Does anybody remember the 2 types of addition we can get with conjugated molecules? Oh man. Remember, we can control it with high heat versus low heat, and we can favor 1,2, or what's the other one? 1,4. So we can get 1,4 addition products. Or we can try to get 1,2 addition. And we can control this using a variety of ways with normal conjugated alkenes. With ketones, it's slightly different. But let's take a look at the overall ketone structure here. We can draw resonance structures where the oxygen has a negative charge and the carbon has a positive charge. Or we can continue with the resonance structures and draw the positive charge out here. So if we think about our electrophilic sites, we've got two different electrophilic sites. So if we throw in a nucleophile into this alpha-beta unsaturated ketone, we have to ask ourselves, which site will it add into? Will it add into the site that used to be the carbonyl carbon, or will it add into the beta position? And so let's take a look at some possibilities here, but let's write down some observations. The first observation that people found when they tested this is that strong nucleophiles will do 1,2 addition. That's another way of saying it will add directly to the carbonyl carbon. And then the other observation was that weak nucleophiles, or weaker, will do 1,4 addition. It'll add to the beta position. Conversely, this beta position attack was a fairly new discovery, and so what they called this was conjugate addition. All right, so let's take a look at some examples of this in action. One really simple test we can do is we can take acetaldehyde, we can treat this with sodium hydroxide, and we can crank up the heat. What will our product be from this reaction? Do you guys want to see the full mechanism for this?
Yes.
Okay, so let's practice the mechanism for our aldol. So we've got some alpha protons over here. Hydroxide can come grab one of these alpha protons. I'm going to actually flip our molecule around. This gives us a negative charge that can be used to add into another equivalent of our starting material that can kick up electrons. Oh, sorry. And then in the next step, we can have water act as our weak acid. Can protonate our alcohol, or our alkoxide. So this is our aldol addition, but we've also created hydroxide And we've got some alpha protons still. So this hydroxide can come around, grab these, clamp down, kick off hydroxide, and we end up with our alpha-beta unsaturated aldehyde. Right? So this is review from our aldol chemistry section. And because this is conjugated, we get some unique reactivity. So one easy test you could do would be to throw in a super strong nucleophile. And in this case, a good example of this would be, let's take a lithiate and then quench it with acid. Lithiates are even stronger than Grignards in terms of their nucleophilic ability. So where will it add? Yeah, it'll add directly to the carbonyl carbon. So this is exactly what you would expect for what we've seen up to now. Let me actually bend this over. Your R group will add in, you'll end up with an alcohol, and the double bond will just kind of hang out over there. Conversely, we can try to use a more gentle alkylating agent. What was the one we saw for alkylating an acid halide without over-alkylating it? Yeah, lithium dialkyl cuprate was the one we used to avoid over-alkylation. And then again, we can quench this with water. And if we do this, we don't attack our aldehyde, but rather we attack our beta position. So this would be an example of 1,4 or conjugate addition. This would be an example of 1,2 addition. And we said that conjugate addition is favored by weaker nucleophiles. Whereas 1,2 addition is favored by strong nucleophiles. All right, I think that's where we're going to leave off today. We're going to expand on this quite a bit, not tomorrow, because we don't have class, on Monday, and we'll jump into our section on Michael addition chemistry. For your lab reports, make sure that you have them handed in by Friday. For notebooks, I realize that you guys have to prepare your lab notebooks for next week. So what we'll do is next week during lab, have your notebooks entirely ready, and I'm going to come around and check them during lab and try to get through as many as I can during lab.